Hello, welcome to our project presentation for EEE 475 Medical Reconstruction and Processing. In our project, we have used scan-specific artifact reduction in case space, and this is our group members. In this presentation, we will start with our introduction and background and methods, then move on to our data and experimental setup and our evaluation methods, and finally finish up with the results and the discussion. Now let us start with the introduction. In our project, we have used scan-specific artifact reconstruction in case space, or namely, the Spark. Spark is an algorithm to reduce and eliminate the errors occurred during the case space reconstruction. In our project, we have worked with different acceleration factors, with different calibration region sizes, and we have used grappa with Spark, rakı, residual rakı, and residual rakı with the Spark. Inherently, MRI acquisition is very slow, and fully sampling the case space takes a really long time. Accelerated MRI undersamples the case space to reduce scan time, but it causes problems such as the residual artifacts. There are some methods to fix these problems, but they are flawed too. Grappa performance decreases at high acceleration factors, causes residual artifacts, or some CNN network uh, do give better results, but they need large datasets or long training procedures. But Spark can do, but Spark doesn't need those. It can improve the accelerated MRI reconstruction quality, reduce the residual artifacts left by the grappa and similar methods, and it combines scan-specific deep learning with physics-based reconstruction. Spark, instead of reconstructing the missing lines, it starts with the existing reconstruction, then learns the reconstruction error and corrects it in the case space. The network is only trained using the ACS and the current scan data. So now let's us briefly discuss the methods. And first, we acquire the undersampled multi-coil case space. Then reconstruct our image using grappa or some similar method. Then the CNN learns the difference between the measured ACS data and the reconstructed ACS data. Then it estimates the residual and it gets added back to the reconstructed case space. Then we finally generate the corrected MRI image, and this is our method.
Data and experimental setup. We use the original data that comes with the paper itself, which contains case space data that is acquired by 32 parallel coils, which with the resolution 236 by 188 pixels. To simulate undersampling the acceleration factor, we undersampled the data by ourselves manually. The case space data contains the whole image, and we performed undersampling only in phase encoding direction. The original paper focuses on factors 5 and 6 and tests different calibration region sizes, which are 20, 24, 30, 36, and 40. And mainly two reconstruction methods with addition of Spark is tested, which are grappa and RAKI. And also, in addition to these two, another version of RAKI, residual RAKI, is tested with Spark. The original code was not able to run on Colab because of insufficient memory. We had to change parameters of PyTorch in order to make it be able to run on Google Colab. Also, the original paper didn't test the Spark with acceleration factors 2, 3, and 4. We also tested these acceleration factors. How did we evaluate the results? We used structural similarity index and peak signal to noise ratio, which we are already using in our course. And also, this indexes was not in the original paper. The original paper only had RMSE, root mean square error, which is also part of PSNR. In order to do these mathematical indexes, we investigated the results by our eyes and checked for artifacts, the visible noise, and another quantitative differences, and made comments about it. The reference image looks like this, and it is generated by full case space and reconstructed by optimally weighted linear combination method. And also the image is included in the data provided with the case space.
Now I will be moving on to the results. Firstly, we have the grappa reconstructions. We can see grappa is not that affected by changes in calibration region size, and the errors are mostly noise with the exception of tiny aliasing artifacts. But these can be improved even further using Spark. In Spark, we can see that the errors are decreased, and again, it's mostly noise with tiny aliasing artifacts. But in contrast to this, rakı struggles very much at higher acceleration factors or low calibration region sizes, and we can see significant aliasing artifacts. Residual rakı is better than rakı in this case, but we can again see significant aliasing artifacts in most cases, and the noise is really worse compared to the Spark case. We can apply Spark on top of these reconstructions to obtain these results. Again, these results are very nice compared to residual Raku or Raku by itself. We have artifacts here and there, but the error is again mostly noise in this case. We have assembled all of the quantitative metrics into a table, but we will be summarizing these as well, but you can pause the video if you'd like to take a look at the values. We can see that Raku and residual Raku are really affected by low calibration region sizes, and we can see Spark-based methods outperform the other methods consistently. This is again the case where we look at acceleration factors. We can see Spark-based methods outperforming the others, but we see a general downward trend with respect to acceleration values. But this is not the only criteria. We also care about the computational times, since the main aim of undersampling is reducing the time of imaging. We can see Spark is much shorter compared to other Raku-based results, and residual Raku and Spark is almost 5 times the time of Grappa and Spark. But as we said, the change in performance is simply not there, so Grappa and Spark is the shortest neural network dependent method in this case.
I will quickly run the Python code for the project to demonstrate that we have successfully replicated the results in the study. So we need to open Windows subsystem for Linux first. And then we run the code that I've prepared in advance. We activate the environment and we go to the path, and then we run the file. For example, we are running residual Raku and Spark code right now. So let's go ahead. As you can see, it's importing TensorFlow right now, and afterwards it will do residual Raku reconstructions. It skipped those because we have already run the code in advance, so it has the files already. And it also skipped Spark reconstructions as well, since we've also run that as well. And it's combining all of the reconstructions into a single file. And after that is done, it will save to a Nocta.mat file. And as you can see, we've successfully implemented the study.
Now we will present the discussion part. We have conducted 125 different reconstructions by using different methods, ACA size, and acceleration factor values. Let's look at the theoretical background first. As we increase the acceleration factor value, we expect fewer case space lines to contribute to the reconstruction and more to be estimated, resulting in a more ill-conditioned image quality. And as we increase the ACA size, we expect the fully sampled calibration region at the center to increase, resulting in a more accurate case space data and better image quality. When we look at our experimental data, we observed that with the error maps and the numerical values that our results aligns with the experimental data. And as we increase the acceleration factor, the image quality worsens. And as we increase the ACA size, the image quality gets better. When we add Spark to the pre-existing Grappa and residual Raku, we expect the computation time to increase and the image quality to become better. And this is also supported with our experimental data. When we look at the 3 basic reconstruction methods, we expect Grappa to be the fastest one, since it's a linear kernel-based reconstruction, whereas Raku and residual Raku are CNN trainings. And the order of these computations times are as expected. When we look at the comparison with the article, we see that the acceleration factors effects and the ACS region size effects are aligns with the article and the theoretical background. In the article, the Spark's improvement on residual Raku was clearer and stronger, whereas in our experimental data, it is more similar to the Grappa and Spark. In the article, they focused on higher acceleration values. However, we focused on lower acceleration values as well. When we look at the computation time differences, we observe that the times are different. It can be because of the hardware implementation and setup differences. However, the ordering of the reconstruction methods computations times were the same. The successful parts of this method is that Sparks improved the reconstruction quality of the Grappa and residual Raku, and it reduced the noise like residual errors and aliasing artifacts. It also aligns the acceleration factor and ACA size effects with the theoretical expectation. When we look at the unsuccessful part, we see that it worked better with Grappa rather than the residual Raku, and some metric changes were not fully consistent. And when we look at the limitations and disadvantages, Spark assumes that the ACA region errors represents the errors outside the region, and it requires CNN training for the each scan, and it takes more time. It only focuses on undersampling in phase encoding direction, and it is a correction method rather than a different reconstruction method. And the disadvantages are it's slower than normal classical reconstruction methods. It takes more computational time, and its performance depends on the training parameters and ACA size. Um, for the future works, it can be tested with different reconstruction methods as VC grappa, Lorax, and 3D grappa, and different undersampling geometries such as 2D acceleration can be tested. Optimization of the time can be tried by using different CPU acceleration, cold compression, or lighter CNNs, and more realistic clinical data can be tested. These are our references. Thank you for listening and for your attention.